Okay, let's just remind ourselves where we were from last time. We were talking about universal source coding. So, we looked at a couple of methods. The main idea was that if we had, if we have a source x, we know that x is IID, independent and identically distributed, but what we don't know is we don't know the probability of 1 and 0. We took a couple of approaches to this. The first approach was to say, what would happen if we just took a string of x, x1, x2, and so on up to xn. By the way, x, we're assuming is binary. We take a string of x from 1 to n. What we're going to do is we're going to count the number of ones. We're going to use the possible number of ones could be anywhere from 0 to n. In other words, there could be 0 ones, everything here is 0. There could be n ones, everything is 1, and anything in between. So we can use, in that, from 0 to n inclusive, there are n plus 1 possibilities. So we could use ceiling log 2 n plus 1 bits to encode the number of ones. And then for each number of ones, we know that there are a finite number of possibilities. The number of ways of arranging k ones in n bits is simply n choose k. So then we could use, once we know the number of ones, we can then use log n choose k bits to encode locations of the ones. And what we showed was that as n goes to infinity, the penalty over entropy is on the order of penalty over entropy is on the order of log 1 over n log n. So in other words, the penalty vanishes. The 1 over n log n comes from this term. So basically, the number of bits you're using in total is ceiling log n plus 1 plus ceiling log n choose k. And we showed that there's both the lower and upper bound for n choose k that's based on entropy. And using that, we showed that this is actually equal to n times entropy plus log n, plus a term in log n, plus a bunch of terms that are order 1. So those vanish as n goes to infinity. And then if you want per source letter, the penalty over entropy is order 1 over n log n. Our next approach was to say, okay, if you don't know the entire sequence at once, or actually, more appropriately, this encoding right here is obviously quite complex. To define a code for each k with n choose k members is not practical for any large n or k. So for instance, think of 500 choose 200. This is an enormous number. What we suggested that we do instead was find a probability distribution call it Q. So I don't know what the probability distribution is, but let's just, let's make one up. Let's make up a distribution Q. And then we know we have two methods of encoding sources if I know the probabilities. They are the Huffman procedure and the Shannon-Fano-Elias procedure, both of which require that I know a probability. So I don't know the probability, but let's assume that this is true. So what I showed was that if you use, basically the assumption was that this is what you don't know. What you don't know is probability x equals 1. And what we assumed was that this was distributed uniform on 0, 0, 1. We don't know what it is, but we assume it's a random variable. And we assume that it's uniform from 0 to 1. And if we do that, it turns out this unknown, or this probability density, this probability mass function has a very simple form. We went through this entire derivation last class, but this turns out to be equal to 1 over n plus 1 times 1 over n choose k, where n is this length, is the length of the vector that you're trying to compress, and k is the number of ones in the vector. We also showed that when you do this, you get the cost of encoding anything with this length. Remember, we have these tools that we can use. If we have a valid probability, we can argue that we can form a prefix code with code words that are length log 1 over that probability, and therefore we can get bounds on the optimal prefix code, the length of the optimal prefix code. And we showed that the length was similar. So basically if we use this strategy, or the strategy of counting the number of ones and then encoding each possible number of ones differently, we showed that it was the same. The cost of encoding was the same. So therefore your cost over entropy, it was the same within order log 1 over n. Excuse me, it was the same within order 1 over n log n. So therefore you don't really lose anything by going this route. So now we're actually going to show that you can encode sequences with a universal source code using an arithmetic code as a universal source code. And we're going to use this method. So remember what we did with an arithmetic source code. An arithmetic code is basically an extended Shannon-Fano-Elias code. And we went through some fairly detailed explanations as to how to obtain an arithmetic code. So now we're going to take this probability density function and use it with an arithmetic code in order to compress a source that we don't know the initial probabilities of. So what would be nice, what we have is this Q. Q, x1, x2, and so on up to xn. Now, remember, if we have a probability, one thing that made the arithmetic code easy to find was that there was a sequential form of this probability. In other words, if I have some probability from 1 to n minus 1, the probability from x1 to xn, if everything is IID, this is the probability from x1 to xn minus 1 times the probability of xn. So this sets up a nice sequential form. Basically, the probability of a single element of this vector is probability x1. Probability of two elements is probability x1 times x2. Of 3 is probability x1, probability x2, probability x3, and so on. Where in each case, we're simply using the probability of the next shorter vector. So I take this, multiplied by probability x2. Take this, multiplied by probability of x3.